So in this lesson, we were introduced to a few different types of transformations. So we had translations, which all points move in the same direction. So if we take a translation, we're going to have a triangle. Let's say we've got this triangle, and we're going to move that triangle over and up in some direction. So that's our translation. All the points move the same distance and direction. So that's a translation. So we can have some special notation if we have a point. Let's say our transformation here, let's say this is the point like 2, 3, and maybe it moved right 4, that would put it at 6, and up 1, that would put it at 4. Okay, we would say, we could write that as a rule, and we could say x, y goes to x, and my little example here went right 4, and the y went up 1. Now let's look at a rotation here. So if we have a rotation takes an object like this here. We've got a triangle and we want to rotate around a point. So it takes all the points and it rotates them a certain number of degrees around a point. And so here we kind of rotated this. This way would be counterclockwise. Okay, clockwise would go to the other way, and counterclockwise goes to the right, actually to the left, we would call this. And we would call this a 90-degree rotation. And the reason why we got a 90-degree rotation here is because if we connect this center of rotation, we call this the center. Whoops. Let's see if we can leave that alone there. So let's go center of rotation. And if we look at a point like this point there, and we look at where it came from. So there we got that there. And it came from here. That gives us a 90-degree angle. Okay? So a quarter turn would be 90 degrees. All right, we'll work more on that. So that's a rotation. We know a couple things. We know that all points are the same distance from the center, and we also know they move through the same angle. So all those points have moved 90 degrees there. Okay, they all swing around 90 degrees. All right, and lastly, we got a reflection. So a reflection, we're going to take an image here, and we're going to reflect across a line. All right, so let's think about that real quick. So if we take this triangle here and we want to reflect it across the line, that means we're going to flip it across this line. And let's see if we can flip that like this. There we go. And we have the original image and the new one. All right. And notice they reflected, so they traveled perpendicular or 90 degrees across. And it goes the same distance. And that's how we mark the same distance. Okay, the distance from the line of reflection. So a reflection will take all points the same distance across the line. So all the points have moved across the line of reflection on a perpendicular line. Perpendicular means 90 degrees. And they're the same distance from that line, all right? So they move perpendicular across the line, and they have to be the same distance. And it turns out that the image will flip. So that's what a reflection does, okay? So we have 3 transformations here. We've got a translation, we got a rotation, and a reflection, okay? Now, what's similar about these transformations? Well, what do you notice about the shapes? When the shapes move, does the shape change size? Nope, it doesn't. So we can say that the image and the pre-image are the same size, and we have a name for that. We call that congruent. So when the shapes move with a translation, rotation, or reflection, they are the same size, they are congruent. So these are the big ideas of what we learned in this section. So some vocabulary real quickly. This word congruent, we're going to use this a whole lot. And so congruent means that two figures are defined to be congruent by a sequence of rigid motions. So if we have these rigid motions, okay, and rigid just means they don't change shape. Okay, so rigid motions mean they don't change shape. That's using translations, rotations, or reflections. And we say that it carries one onto the other. Okay, the symbol we use is congruent. So if we can come up with some transformations to move one to the other, that means it's congruent. And we got this idea of pre-image and image. Okay, the pre-image is the original figure there, and the image is the new figure. All right, so image is new. Okay, so from one to the other, we get the image is the new. All right. We got orientation is a word we'll use a bit there. Okay, that has to do with the order in which a figure's vertices are labeled. All right. So we take a triangle, for example, and if we label this A, B, C, okay, the orientation would be kind of the order we could name this in. A, B, C. We would call this triangle A, B, C. Okay, so we got these rigid transformations, as what we call these. These three transformations are rigid. They're rigid because they don't change the shape. So it just means that the pre-image is the same as the image. The pre-image and the image are congruent. That's the big idea. Okay, so it's rigid if they're both congruent. Okay, and when we have rotations, we're going to have concentric circles. Concentric circles just means we have circles with the same center. Okay, so let's make some circles here just for example. Okay, so if we have a little circle like this, and we got another circle like this. Let's see, I better make it like this. Okay, here's another circle. There we go. Okay, so if these two circles have the same center, let's see if we can make it like that. Well, let's pretend they have the same center. Okay, if they have the same center, then they are concentric circle. Common center. Okay, so there's the big ideas. Okay, that's what we learned in section 1.1. Next, we'll take a quick look at a few other concepts that we'll be using in our practice assignments. So just to kind of see what's going on here, when we have this translation here, translation, if we connect the corresponding points, then we get these nice parallel lines. Okay, so this is a translation, and so the translation makes parallel lines. These retrievals are our kind of looking back at things that hopefully we've seen before. This is a right triangle. When we're looking for the missing side of a right triangle, maybe we'll call this B, we'll call this side A, and this is the hypotenuse. So the hypotenuse is the longest side of a right triangle, and we're going to be using the Pythagorean theorem a lot. And the Pythagorean theorem has to do only with right triangles. So the Pythagorean theorem says when we have a right triangle that the length of the two legs squared, these are called legs, the two sides that make the right angles, A and B. Those are legs. A squared plus B squared equals C squared. So those lengths, the length of the two legs squared, add up to the length of the hypotenuse squared. So if we know some of those, like we know A here is 3. A is just one of the legs. We don't know this other leg, so let's just leave it alone. We do know that the hypotenuse C is 6. So we have 6 squared. So we put those in A, B, and C. A, B, and C in our formula. So this formula, super important here. All right, we're going to be using that a lot. One of the most important theorems, if not the most important equation in geometry for sure. So we can solve this just using our algebra. So this is 9 plus b squared equals 6 squared is 36. Now we got to get that b squared all by itself. Remember from algebra, you want to get the variable by itself. 36 minus 9 is 27. And the opposite of squaring is square rooting. So we're going to square root this. And now we've got to use a calculator to get a decimal value. We get the square root of 27, which there is no number that you can square to get 27 exactly. And so that gives us 5.196. Okay. Now the exact answer is the square root of 27. So this is something that we'll be working on more. That's exact. And this is called an approximate. Because when you plug in your calculator, you got to round it off a little bit to get 5.196. So that's how we find the missing side of a right triangle. Okay? All right, one more little review topic and then we're done here. So graphing, this is, remember this function notation, f of x? F of x is the same thing as y. So if it helps, you can rewrite this equation as y equals 2/3 x minus 1. Now if you want, you can make a table of values for this, now, this is in slope-intercept form. Y equals mx plus b, and m tells us the slope, and slope is rise over run, remember that? And b tells us the y-intercept. So b is the y-intercept. So the y-intercept is where the graph crosses the y-axis, and the slope tells us the steepness, the rise and the run. Well, what is the y-intercept? Well, the y-intercept here is -1. So that's where it crosses the y-axis. So we've got our graph. It crosses at -1. Okay. In your assignment, you'll be drawing some of these in, but this one's drawn in. That's nice. So we got -1 there. And then we've got a slope 2/3. So 2/3 is our rise over our run. So for this particular graph, we've got 2/3. That means from one point to the next, we're going to go up 2 and a run of 3. And that gives us a new point. And then we can go from that point up 2 and over 3. And that tells us we got another point over here. And if we wanted to, we could go left 3 and down 2. That would find another point. Okay? So these are all points on the line. So we can draw the line. This line goes on forever. So it's best to go ahead and put arrows on the end of it. And there's the graph of your line. Okay, so there's a quick review on slope-intercept form. So slope-intercept form, again, slope-intercept form. This is something you want to remember, something for your note catcher. Y equals mx plus b. That's going to be a really important equation to learn and use throughout your math classes to come. So, okay, so a couple of real important equations: Pythagorean theorem and slope-intercept form, y equals mx plus b. So there is a good recap for you on all those things that we're going to be using. Thanks for watching.